Hi everybody, this is Mr. Short. Today what we're going to do is we're going to explain the relationship between VSEPR and molecular geometry. So I want you to start by taking these brief notes down at the bottom. You can see I color-coded the acronym VSEPR up here and the acronym VSEPR right down here. VSEPR stands for Valence Shell Electron Pair Repulsion Theory, and you're going to explore that inside your POJL. But I want you really to focus on the last three letters, the E, P, and R. The EPR stands for this. Electron pairs will R repel from other electron pairs. Why is that? Well, pairs of electrons are negatively charged. And you all know that like charges repel. So a negatively charged pair of electrons will R repel from other negatively charged pairs of electrons, forcing molecules into particular geometric shapes. Okay, and that's the concept that we're going to explore today in this packet. So you might want to hit the pause button right now and get those notes written down. Okay, from our molecular geometry POJL packet, we've already completed a little bit of this packet, but I want to do a brief little review with you. Remember, we're familiar with how to draw Lewis structures. Remember, there are 5 steps for drawing Lewis structures. Step 1 is the accounting, how many valence electrons are going to be in the final structure. Step 2 is the skeleton structure. Step 3 is 6 more electron dots to everything but not the central atom and never to hydrogen. Step 4 says that leftover pairs of electrons will go on the central atom. Step 5 basically asks the question, is everything following the octet rule, with the exception of hydrogen? If not, then you need to cross out and share to form multiple bonds. And then also, if you've got a charged polyatomic ion, you need to put brackets around it with the charge in the upper right-hand corner. So whenever you're drawing Lewis structures, you need to follow those 5 steps. The other day, we also explored bonding domains and non-bonding domains. And we said that a bonding domain looks like this. And it doesn't matter if it's a single, double, or triple covalent bond, they all only count for one bonding domain. That's a concept that you've already explored in this packet. So down here, I want to start focusing on 2 molecules, formaldehyde, which is H2CO, and ammonia, which is NH3. If I flip back and take a look at this table that's at the bottom of page 3, you'll see that there's a table that talks about and explores 3-dimensional molecular shapes. Before we think more about that, I want to point out that in the molecule for formaldehyde, it has 3 bonding domains and 0 non-bonding domains. When I take this information right here over to this table, I can infer that this must be the correct molecular structure, 3-dimensional structure for formaldehyde, because I can spot 1, 2, 3 bonding domains and 0 pairs of non-bonding electrons on the central atom like we've got in these 2 that are right down here. So for that reason, the molecule formaldehyde is called trigonal planar, and it has a 120-degree bond angle. So it looks like this. That's in contrast to the molecule ammonia, which has 3 bonding domains, but 1 pair of non-bonding electrons, therefore 1 non-bonding domain. When I take this information 3 and 1 over here, you can see that ammonia must look like this, and this is called pyramidal. You can see that it's got a 107-degree bond angle. So I took this information and I attempted to draw the 3-dimensional molecular structure in this spot right here. So let's compare and contrast these 2 different shapes. The top one, remember, is called trigonal planar, and it looks like this with a ball and stick molecular modeling kit. The bottom one is called trigonal pyramidal, or just pyramidal. You can see it looks like this. All right, the top one, if I tip it like this and I tilt it just carefully, you can see that this, and this, all 4 atoms are in the single same plane. For that reason, formaldehyde is a flat, 2-dimensional structure. That's in contrast to ammonia. It's a little bit difficult on Zoom to do this, but if you take a look right here and we use this straight edge, the white paper right there, you can see that the green hydrogens are pointing down and the black nitrogen is pointing up. For that reason, this is 3-dimensional, ammonia, but formaldehyde is a flat 2-dimensional structure. So the question that we should ask ourselves is, well, why is this three-dimensional, but this is two-dimensional up here? This works better when I'm in front of students, or at least when I have students on a Zoom call, because we can go through a question and answer session. But ultimately, what students come to the conclusion is, this pair of non-bonding electrons right here is the variable that's different between formaldehyde and ammonium, whereas a constant is the number of bonding domains. So we have to focus on this. And it's right to focus on that. That pair of non-bonding electrons, it repels these, and these electron domains here because all electron domains are always negatively charged. So they want to repel from one another to get as far away from one another as possible. In this case, it maximizes the distance between all domains when it's in a pyramidal configuration like this with a 107-degree bond angle. That's in contrast to this one up here. Distance is maximized between bonding domains here when it's in a flat two-dimensional structure, which is called trigonal planar, with a 120-degree bond angle. So I want to go back to the notes that I presented at the very beginning of this because those notes really tell the story. Remember, the notes are about VSEPR. This is a theory that's used to predict why atoms take particular geometric shapes. And VSEPR basically says that electron pairs will repel from other electron pairs because electron pairs are negative, and so they all want to get as far apart from one another as possible, forcing these things into three-dimensional configurations. So remember, anytime that you're trying to explain why something takes a particular geometric shape, you always need to revert back to the acronym VSEPR and use the acronym VSEPR to explain why something takes a particular geometric shape. Very last thing, we also took this note earlier in the course. This note really supports this right here, but this note by itself doesn't really give an explanation for why. So think about the connection between this note and these notes down here. Okay, so when drawing Lewis structures, we space out bonds and non-bonding electrons as far as possible. Why? Well, it's because electron pairs repel from one another. All right, thanks a lot, guys. Have a great day, and I'll see you soon.